Hi there, and welcome to our Calculus 1 video on limit laws. This is a video in a series of videos on limit laws, probably the last one. So let's take a look. We left off evaluating limits using some algebraic techniques, whether it was a definition of absolute value or LCD. We've also in the past looked at factor and reduce, rationalizing, things of that nature, using all these limit laws. So let's take a look at this question number 6. Okay, in this problem we are asked to find the limit as x approaches -2, the log of this first argument right here, which is a cubic function, minus the log of the second argument. And I'm sure you are familiar with logarithms from your pre-calculus course, but I hope that you will remember we cannot not evaluate things like log of -7, right? Because again, log right now is common log or log base 10. And so we would be suggesting 10 to some power equals -7. And you can't repeatedly multiply or repeatedly divide by 10 and come out with a negative number. So you are not allowed to have a negative number in your argument, as well as you are not allowed to have 0 in your argument. So, because that would be saying log of 0, right, log base 10, let's say, of 0, common logarithm. So we'd be saying 10 to the something is 0. And again, you cannot multiply repeatedly or divide repeatedly, which is what that exponent is telling you to do, and come out with 0. So we have to have a positive value in here. So what I mean by that is this yellow highlighted argument and this blue highlighted argument have to be positive. They have to be, for a domain, greater than 0. So I already see a problem that I'm not going to be able to substitute in -2, but let's give this a further look here. I also should remember if I have log of this yellow minus log of the blue, and they're the same base, these are both common logarithms, I should remember one log property that I can rewrite these as one logarithm. So I can say log of, and it would be the yellow divided by the blue. And if you'll remember from your algebraic pre-calculus course, whether it was pre-calc or college algebra, whatever it was, that when you are working with logarithms, logarithms are really equal to exponents. So that question mark that we had there is this exponent of my base. And so that's why some of these laws or properties of logarithms work. So that's why this subtraction of two logarithms turns into division, because if you think about it, when you're dividing like 10 to the a over 10 to the b, this would be 10 to the a minus b, if you'll remember that from exponent properties. So our log properties follow a similar suit here. So this would be log of the yellow all over the blue. Not log divided by log, right? Because that was not what the property told us. So now if I go to substitute in a -2, let's see what we get. Because maybe I can just substitute this in right away. Probably not, because I can see that that denominator, -2 plus 2, is going to be 0. But it is very important that you calculate that numerator out. All right, so what does my numerator become? -2 cubed would be -8, so this is -16 plus 4, so 12, plus 10 minus 6. So that will be 6, and -6 is also 0. And again, you could use your calculator for some of that computation. Well, 0 over 0 tells me I have some algebra to do, and remember we have 4 basic techniques here of algebra that we're going to be working within. We always want to get to the point where we can substitute, so that's kind of our main goal. So right now I think maybe I'll work with this and see if I can factor that numerator. Now the key here is I know what factor I want to divide to 1. I want this x plus 2 factor to go away. In other words, when x is approaching or equaling -2, I know that this numerator gives me 0, which means I know that it divides in evenly. So I'm going to rewrite this and then show you how I can use that knowledge to really save me some time here. So I know there's already a factor of x plus 2 in the numerator. There has to be, because when I substituted in negative 2 into that numerator, I got 0, which means it divides in evenly. But we can do some synthetic division off to the side and make sure. So I'll take my negative 2 off to the side. I'm going to divide this into 2x cubed. Remember, perfect descending order here. All the coefficients, 3x squared, negative 5x, and negative 6. And we've done synthetic division in a previous video, but here we go. Carry the first number down. This negative 2 on the outside here is my multiplier, so 2 times negative 2 is negative 4. Add down. Negative 1 times negative 2 is 2. Add down. Negative 3 times negative 2 is 6. Add down. I should get 0 because I knew it went in evenly, but here is my quadratic. 2x squared minus 1x minus 3. I can certainly check that. One way that I check it is actually just quickly using my graphing calculator with a random x value. Let me show you. So if I'm just grabbing my graphing calculator and I go to my home screen, let's store something in for x. Maybe it's 5.7, maybe it's 3.9, something not negative 2, okay? Now right above your on is your store, so I'll click store as x. This only stores it for computational purposes on your home screen, so you're good. Now I'm going to type in the red or the original polynomial that I think it was, and then I'm going to type in the factored form and I'm going to see if they're equivalent. So here I just typed in the 2x cubed plus 3x squared minus 5x minus 6, which was the original polynomial there. I got some value here. That value is not necessarily important, but it is important that it's the same as the factored form if I factored it correctly. So I will type in the factored form, making sure I type that in correctly, and nope, that should be a minus 3 there. And I'll hit enter, and I should see the exact same output. Again, that output isn't necessarily important because x approaching 5.7 is not necessarily important to this problem, but it's a pretty good indicator that I factored this correctly. So now I can see my x plus 2 factors divide to 1. Now I should be able to substitute in my negative 2. So since I'm evaluating the limit, I'm not going to write the limit anymore, but I still do have a log out in front of here. So I have 2 times the x was negative 2 quantity squared minus 1 times negative 2 minus 3. So I have the log of, let's see, 4 times 2 is 8 plus 2 minus 3. So this should be log of 7. And I'll show you, we can certainly check this using our calculator, but please recognize that log of 7 is a really ugly, it's like an irrational number if you look at it as a decimal. I think it's beautiful as an exact form, log of 7, but if you're trying to write it out as a decimal, right, it's irrational, so you may not recognize it on a graph. You may also not recognize it on a table of values unless you figure out what its decimal version is. But I highly recommend either checking that using a table of values or using your graph. All right, so let's take a look here at the last problem in this limit laws section. We're really in this section, we are linking together the table of values, the graph, and a lot of your algebra and limit properties or laws that we have learned. So this last one has to deal with the greatest integer function. And this is one notation for that. You might also see it look like something like this. It's also sometimes called a floor function because people like to think of it as a floor. One of the ways I like to talk about the greatest integer function is, let's just say that all change is eliminated from our society. One option for that would be to say that you can't charge $3 for something that is worth $2.99 because it's only worth $2.99. So you'd have to go down to the next closest integer, which would be 2. If something is worth $3.01, well, charge $3. What I want to make sure you know is that this is not proper rounding, okay? So you're not going to say 1.5 or 2.99 will round up to 3. So I'd like you to take a look at this graph that I put over here on the right. We're going to add the points in the holes because, again, if I'm calling this a function, both this, I'll delete this in a second, and this cannot be completed points because that would defy a function. All right, so, or defy the vertical line test, however you want to think of that. So take a look at some of these values here. So as I go along, I'm just going to use from 1 to 2 as an example. If my input is 1, 1.1, 1.2, 1.3, 1.4, 1.5, etc., all the way to 1.9999, the function's output is only 1 because that's the next closest integer less than that value. Now, I didn't name it the greatest integer function, so I apologize for that, but it's the greatest integer that is less than the number that you have. So, just for practice, if we were looking at something like 1.72 greatest integer, we would round that down to 1. And if we were looking at something like 1.01, we would round that down to 1 as well. So it doesn't matter how close we are to 2, anything between 1 and 2 gets rounded down to that next closest integer. So it's the greatest integer that is closest or less than your input. So what happens is when we are 0, we will equal 0. But as we approach 1, this one's going to be a whole because then if your input is 1, now you're up here at 1, 1. So here's my point, whole, point, because 2, 2 should make sense that that's a point, and so forth, okay? Now, I'm not going to ask you, this is also called a step function for some people. This also goes into the negatives. We can look at that later. The pattern just continues here, okay? But what I want you to be able to do is if you see this graph, could you find these limits? Okay, well, limit of my greatest integer function as x approaches 3 from the left. All right, well, let me kind of point out where x equals 3 is to begin with. So here's x equals 3, right, as a vertical line, if you will. And so if I'm approaching x approaching 3 from the left, I'm down here on this part of the curve. My output is 2. And if we would be able to say that, that's really all I need you to know at this point about the greatest integer function. Okay, and if x approaches 3 from the right, well, now I'm still approaching that purplish highlighted line here, but now from the right, I'm up at this point, so that will be a y value of 3. So if I ask you if there is a part C, limit as x approaches 3 of this greatest integer function, what would you say? Hopefully you would say DNE, because the limit as x approaches 3 from the left of my function, and I can call it out, I should say greatest integer function here, does not equal the limit as x approaches 3 from the right of this function. So the one-sided limits are not the same, therefore that limit cannot exist. So I hope that helps. And again, I'm not asking that you're an expert with the greatest integer function, but just hopefully we can expose you to some different piecewise functions that may appear later on. If you need your outputs to be integers, regardless of your input, then this is something that could be helpful. So if your inputs end up, looking something like 1.39, but you're talking about how many people, it might be a whole person, 1, or number of fish in the lake, right? We often will round those to the nearest integer, so this might be a helpful function at that time. I hope you found this helpful. Thanks for watching.